Think about something that evaporates. You're probably thinking about water or milk right now, but what if I told you that black holes evaporate? Hawking radiation is a process in which black holes lose mass and energy. It is named after the physicist Stephen Hawking, who provided a theoretical argument for its existence back in 1974. In order to understand Hawking radiation, we need to understand two things first. 1. What is a black hole? After stars run out of fuel, they explode an explosion called supernova. Supernova occurs when the star loses its energy, which is generated by the nuclear fusion inside its core. This energy keeps fighting gravity to keep the star stable, but when the fusion process reaches its last element, which is iron, this reaction doesn't release energy. Thus, gravity wins and the star collapses, leaving a neutron star, or if the star's mass is high enough, a black hole. So, black holes are objects in space with a very powerful gravity that nothing, not even light, can travel fast enough to escape it. You can't escape black holes after crossing its outside part, which is called the event horizon, which is why it's also called the point of no return. While the inside part of a black hole is singularity, we're not really sure what it is. Anything can be a black hole if it gets to its far stride radius. Earth would have to get to the size of a peanut. The popular belief that black holes are the vacuum cleaner of space is only correct near the event horizon, but far away its gravitational field is not different from any other object in space. In fact, if we replace our sun with the same sized black hole, Earth won't be affected except that it will freeze. Now think about nothingness. This might look empty to you, but there is air and a lot of atoms. Well, space vacuum isn't empty either. There are virtual particles that pop into existence and then immediately annihilate each other because one has positive energy, the other one has negative energy. Think of it as an equation. 1 minus 1 equals 0. There is something on this side, but there's something that cancels it, which is why it still equals 0. Now we're ready to talk about Hawking radiation. What if a pair of virtual particles appeared near the event horizon? When this happens, the virtual particle with negative energy falls into the black hole, while the one with positive energy escapes. Now, the one with positive energy is a real particle now with its own mass and energy, but the other one has negative energy, so it will make the black hole lose mass and energy a little bit. And that's why it's called black hole evaporation. So black holes that aren't gaining mass will lose mass overall, so it gets smaller and its temperature rises. With time, the black hole becomes small with a very high temperature, so it explodes. But this takes so much time that the biggest black hole we know will take a Google years to explode.